Hi, everyone. So hopefully this is working. And so this is the video for abstract algebra. So it's really great class. It's gonna be a lot of fun. Um, so the prerequisites are that you should have taken a proofs class. So I think most people that are taking this are people that took the proofs class last semester. So you'll be well prepared for this. Um, so let me go through the syllabus and we'll try and talk about a few things. This will be pretty short. There we go. Okay, so I just wanted to read the description. So if you've been in my class, it's the same overall routine. Okay, but let's see this topic. Oh, okay, so abstract algebra. So maybe is it just algebra? I mean, isn't algebra already abstract? We'll see. Okay, so in pre-college mathematics courses, we learned the basic methodology and notions of algebra. We appointed letters of the alphabet to abstractly represent unknown or unspecified quantities. We discovered how to translate real-world and often complicated problems into simple equations whose solutions, if they could be found, held the key to greater understanding. But algebra does not end there. Advanced algebra examines the sets of objects, numbers, matrices, polynomials, functions, ideas, and operations on those sets. The approach is typically axiomatic. One assumes a small number of basic properties or axioms and attempts to deduce all of the properties of the mathematical systems from those. Such abstraction allows us to study simultaneously all structures satisfying a given set of axioms and to recognize both their commonalities and their differences. Specific topics to be covered include groups, actions, isomorphism, symmetry, permutations, rings, fields, and applications of these algebraic structures to questions outside of mathematics. The pace and level of discussion is aimed at students who have experienced reading and writing proofs. Okay, so at the end of this, I'm going to just talk about the class. I'm going to talk about a few of these topics like rings, groups. Yeah, so we last semester we were sort of in the quicksand or the clouds, I don't know, uh, of the axioms of, we talk about the axioms of set theory sometimes, and so I like the axioms of math or the axioms of set theory. Um, those we can't prove it can't prove its own consistency. It's a little bit shaky ground. It's a little bit wild, but this will be a little bit safer. We're in a world that's like these definitions that we have are axiomatic definitions, and yeah, so we're not going to be dealing with like incompleteness or anything like that. But it's very fun, a very enjoyable if you like writing proofs, if you like um, linear algebra. If you like it's like so we look at the idea is like we look at the integers and look at the operation of addition on the integers, and you can see, okay, if you add two integers you get an integer. Okay, maybe I'll stop the share for a second. Okay, so if you add two integers you get an integer. Every integer has like an additive inverse. So 2 plus -2 is 0. And that 0 is like an additive identity. So 0 plus 5 is 5. So the idea is then we look at the properties that integers plus addition satisfy, and then we try and find other things that we take that general concept of what the integers are doing with addition, try and find other structures that are like that. Okay. So we start with something that we know, like you know how the real numbers work, how you can multiply and add them, and you know about multiplicative inverses of real numbers, you know about multiplicative inverses of rational numbers. And so the idea is that we take these things that we already know, sort of break it down, and it's like, well, what is the actual um, properties of this structure, and then we try and find other structures that have those same properties. Okay. But the structures that we might be working with um, that have these properties that are a group or something, they might be like functions or matrices, um, polynomials. Okay, so kind of like in linear algebra, when we talk about what a vector is, and so it's this arrow, but it also could be a matrice. It could be a tuple. That's it. So this is very similar to that idea. Okay, so let's go back to the share. Okay. So I really think that if you like any kind of abstract math elective class. Okay, I'm still in the science center 323, I think, and put that on there. The textbook definitely should get the textbook. We can see if we can find an online version. First course in abstract algebra, John Fraley, and that's the book. And so we'll be just one book, and we'll talk about the schedule once we all get the book. Okay, mine should be coming soon. Uh, uh, so course quizzes, so there'll be at least 2 in-class quizzes. I have tried in the past to do like multiple quizzes, but I feel like it's kind of breaks up the flow of the class. So I think the 2 are good, and there's usually a take-home portion of that, and we always have a review of some kind. Okay, but most of the stuff happens in class, just the regular day-to-day class. Attendance is so important, and you really help yourself out if you come to every class. I really appreciate when students can come to every class. I know things happen, of course. Um, but so seminar and conference attendance is mandatory. If you miss more than 2 classes, it says reduced course credit or could lower your grade. This is important. So if a class is missed, students are responsible for obtaining class notes and assignments, and then you're expected to be fully prepared for the next class. Okay. In some cases, I might be able to send you the notes or something if it's like you have COVID or something. But in general, if you miss class, just get the notes from someone or figure out a way. Because if you ask me, then I might say something like, "Well, it will take me an hour and a half to explain what we did in that class." Okay, so in general, I think it's best to just, if you miss a class, figure out for yourself, get caught up. Okay. um, yeah, this all meet for conferences, and generally it's hard to reschedule a missed conference for me because my schedule's busy with uh, each week with meetings of students. So yeah, well, we can work that out. And also something I add this semester to this syllabus is that part of attendance includes paying attention in class and not disturbing the peace of the class. So there's plenty of time in class where you could talk to people, work together. But I really appreciate when I'm at the board that everyone's that you're quiet and like not listening to each other. It's really distracting, and I think it distracts the rest of the class. I just like a peaceful vibe in the class, and yeah, it's a little bit laid back, but that doesn't mean that it's like anything goes. Okay, and so I think that that's pretty clear, but I just want to make sure that it is clear. Um, yeah, I want to have a fun class, but I also want to make sure that it's like nice and peaceful when I'm presenting, because it's high level thought, and so I have to not get really distracted. The sounds. Okay. Anyway, I think y'all know how to be in a math class or any class. Um, and we'll also do lots of problems in class, and there'll be plenty of opportunities to write the board and work together. And I love when students like write the board and just solve the problems themselves. And when we have time in class to do that, I know we don't have time to do that in class. But when we do, it's really great. I hope that the students enjoy as well. Conference work, I loved conferences. I've always had just really positive experience with students in conferences. I think it's really important that you pick something that you're interested in, but it has to be something that if you're really interested in it, that you have to be. If I'm not knowledgeable in it, then you have to be knowledgeable. So, like for example, a student used Blender to create some really cool objects. I don't know anything about Blender, but they did. So, or you could pick something that I'm interested in, like art or set theory or some math. Okay, or pick something that we're both interested in. I love art projects. Would love like a poem or something, anything. But also you can do history. You can do people have done portraits of mathematicians and done important proofs by that mathematician. There are all kinds of options, and just we'll talk about it. Okay, additional help. There's a great tutor. Is there a tutor for this class? I don't know. But there is. That's actually a good question. I'm not sure if there's a tutor for this class. Okay, evaluations at the end of the semester. I give evaluations. I basically just say how many classes you missed, how you did on the quizzes, your classroom behavior, and then how you did on the conference, and like how you participate in class. Be really straightforward. I think it's straightforward. Okay, student support. I'm always happy to support students. I try and make my exams so that everyone can finish in plenty of time, or I don't like a lot of stress surrounding exams, but I do think that exams are important. I think the best is for you to go in like fully prepared and in a lower stress environment and just do well. Okay. Science, math, third programs. Okay, I think you all know about all this stuff. Academic integrity is very important. Okay. So let me stop the share real quick. I am just going to mention a few things. Okay. I have like a whiteboard, but I'll also mention a few things just so you can start thinking about that. Okay. So the things I want to talk about are what is a ring, a field, and a group. Okay, just to mention, and I'm gonna give you some homework. Okay, so a ring uh, is a set. So you know what a set is with two binary operations, and we call them addition and multiplication. But it might not be the actual addition and multiplication that we think of. And they have all the properties analogous with those of like multiplication and addition of integers. So you can think of, for example, of a ring, think of the integers, z, the integers plus just regular addition and regular multiplication. So, and you think about that, and think about what's there and what's not there. Okay, if I add two integers, I get an integer. If I multiply two integers, I get an integer. If every integer has an additive inverse, 5 plus negative 5 is 0. So, and 0 is a additive identity. But notice it doesn't have, rings don't necessarily have a multiplicative inverse or a multiplicative identity. And so that was like, what do I multiply 2 by to get 1? Okay. So a ring is like a generalization of a field. And so a field is like, this is what we like, what we think of in math as like our structure that we use. It's like the real numbers plus multiplication and addition. So a field is like what we would think of like the real number, just the real numbers with addition and multiplication. And you can think about what are all the properties of the real numbers with addition and multiplication. Okay, everything has an additive inverse, everything has a multiplicative inverse this time. There's additive identity, multiplicative identity. Okay, so it has associativity, commutativity, like a plus b equals b plus a, or 2 plus 3 equals 3 plus 2, etc. Whereas a ring doesn't necessarily have to have that commutativity. So it's a generalization of a field. If a ring does have commutativity, then it's called an abelian ring. Okay. Okay. So I'm just giving you these words so because they're going to come up just for fun. Group, and so a group, both of those, a ring and a field, have two operations: addition and multiplication. A group just has a set plus one operation. It's usually written as the plus symbol. It's supposed to imitate. I mean, it's supposed to be like a generalization of plus. So so we'll call it addition or the plus symbol. So it's closed under this operation, this binary operation. So if you add two elements, they stay in the group. It's associative. Their identity exists, and every element has an inverse. So it's like a ring, except you don't have the extra operation of multiplication. So an example of a group is like the integers with addition. So just think about one of those properties, and then maybe think about, is there some structure that kind of looks like it has the same structure as or satisfies the same properties as the integers. And there are lots of things that are groups. Okay, so one thing I want you to think about, this is your homework, is think about the square, just a square, and think about the elements of our group are going to be the symmetries of the square, things that you can do to a square that keep it just a square. So if I have a square, I could rotate it 90 degrees, and it's still a square. So let's call that R1. Square, I rotate it 180 degrees, still a square. Let's call that R2. R3 would be 270 degrees. What else could we do? We could just keep it in place. We could flip diagonally this way, flip diagonally this way, right? We could flip this way, flip vertically. Okay, so think about all those operations that you can do to a square to keep it a square. Okay, so, oops. Okay, so I want you to make like a chart. So think about all the operations of the square and put all your, give them names. So I gave them R1, R2, R3, maybe F, flip one, flip vertically, flip horizontally, and then the two diagonals. And then make a table, put all your, so this is the binary operation is we're going to do one right after the other composition. So put put all your symmetries here, and then put all the symmetries here, and then combine them and see what you get when you combine them. Okay, so for example, if I do R1 plus another R1, I get R2, right? So composing R1 with R1 in the table, you'd get R2. Okay, so I want you to make that table. Okay, what do you think about that? And okay, so think about that, and we'll talk about it when we get back to class. Okay, and I really look forward to this class, and so I hope to see you there, and hope you have a great rest of the winter break. And I don't know if you can see my cat there. There he is, Mr. Zeke. He's more of a physics guy than a math guy. But okay, see you guys later.